In this example of Newton's second law, we have a coupled system. So a system that involves two blocks that are connected together by a cord, and they rest on a frictionless surface. If a force of 20 newtons is applied to the first block as shown in the picture, we want to determine the tension in the cord that's connecting the blocks and also the acceleration of this system. And we're going to use the information that's in the picture. So there is no friction, which makes this problem a little bit easier. And so when you have a system that involves more than one object, it's often a good idea to look at the system as a whole first, and then go back and look at each of the individual objects. So what that means is that we are going to start off and we are going to look at this whole, both blocks, as our system. So we can imagine that everything that is surrounded there by that block that I drew is part of the system, is inside that box, and we can't really see that inside that box. So everything inside there that's going on is internal to the system. So the only thing that's external to our system is this applied force. And then, of course, the two blocks are actually in contact with the ground, and we have the force of gravity. So if I were going to look at this as my system, I can draw a free body diagram of my system. And I guess I should back up for a minute. So we already have our coordinate system, which has been provided, right? So we have an x direction, which is horizontal to the ground, and then the y direction, which is vertical. And we're asked to find the acceleration of the system, and that's been drawn in our picture for us as well. If you have a system like this, it's likely moving across the floor, so the acceleration is going to be in the x direction. So the acceleration in the y direction is 0, and the acceleration in the x direction is what we're looking for, this acceleration a. So there's no movement up or down, and that's why the acceleration in the y direction would be 0. So let's draw our free body diagram of this system. So if I were drawing a free body diagram of the system, I would have the force of gravity that's acting. This is the force of gravity of my system. So this is the total mass, and so the total mass of the system is just the masses added together. 4 plus 6 is 10. So this is going to be 10 kilograms. So if I find the force of gravity of my system, it's 10 kilograms times 9.8 meters per second squared. So my force of gravity is going to be 98 newtons. I also have an upward force that's a normal force, which is the force of the ground on my system. And you'll notice that I did not draw it as large as the force of gravity. And that's because I'm thinking ahead just a little bit. And I'm thinking about the fact that this 20 Newton force that's applied to the system has to be resolved into components. And it will have a component in the x direction, and it will have a component in the y direction. And because I know the angle here is 30 degrees, and I know the hypotenuse is 20, the x component is 20 newtons times the cosine of 30 degrees. And the y component is going to be 20 newtons times the sine of 30 degrees. And that is really hard to read. So let's do a little bit of erasing here. So the y component right here is going to be 20 newtons times the sine of 30 degrees. All right, so now I can draw those forces into my system. So I have my force in the x direction, which is 20 newtons times the cosine of 30 degrees. And then I have part of that force, which is lifting the block up, which is 20 newtons times the sine of 30 degrees. So looking at that as my system, I now have only one external force that's acting along the x direction. There's my x direction, there's my y direction. And the only force that's acting along the x direction on my system is the component of that applied force. So if I look at the sum of the forces on my system in the x direction, it has to equal the total mass of my system times the acceleration. The only force acting external to the system is this 20 Newton force that's acting along the x direction, so 20 newtons times cosine. My mass is 10 kilograms, and I can now solve for the acceleration. So if I plug in 20 times cosine of 30, I get 17.32. And then if I divide both sides by 10, I can determine what the acceleration is. So the acceleration of my system is 1.7, I'll write it out, 32 meters per second squared. Now because the blocks are connected together, they move together. So whatever the acceleration is of my system, this is also the acceleration in the x direction of block 1, and it's also the acceleration in the x direction of block 2, right? They have the same acceleration throughout because they move together. Now, we weren't asked to actually determine what the normal force was here, but we could do that if we wanted to. Just to write it out, I didn't actually do all the numbers here, but I could do the sum of the forces in the y direction on my system. And I'm going to go ahead and put system on here. They have to be 0, so as I look at my free body diagram, I have the force of the ground on the system acting up. I have that 20 Newton force that's in the y direction, which is 20 times the sine of 30. And then acting down, I have the force of gravity. So 20 times sine of 30, I guess I actually did calculate that, is 10. Minus 98 is 0. So if I move things around, 98 minus 10 is negative 88. And then if I move it to the other side, I get that the normal force has to be 88 newtons. So I have actually answered part B of this question first, the acceleration of the system. It's just a nice way to do it because I didn't have to worry about the tension at this point, which was unknown. And regardless of which of those masses I looked at, if I looked at them individually, I would have to have known what the tension was to solve for the acceleration. So that leads us to part A. So I want to know what the tension is. So in order to solve for the tension, I have to go, and I can't look at the system as a whole, I have to look at one of the masses. So I'm going to now erase this big box, and I am going to have a new system that I'm going to look at. So now I'm going to focus on just mass 2. I'm choosing mass 2 because mass 2 only has one force acting on it in the x direction. So let's draw a free body diagram for mass 2. So as I look at mass 2, the forces that I have acting on it would be the tension, which is pulling it to the right. I would have the force of gravity on 2, which is the mass of 2 times gravity. So this is 4 kilograms times 9.8 meters per second squared. So that's going to be 39.2 newtons. And I also have the normal force, which is the force of the ground on 2. Those are the only forces I have acting on mass 2, right? So this is just for this particular mass. I certainly could have looked at mass 1 and it would still work. It's just that there are more forces acting on mass 1. So the other thing that I do know is that this mass is accelerating. There is an acceleration of this mass in the x direction, and we found that it was 1.732 meters per second squared. So we know that there is some net force, and that net force that's acting is the tension. So I'm going to move this up now, and I can focus just on my mass 2. which is 4 kilograms. And I can look at my free body diagram, and I can look at the sum of the forces on 2 in the x direction. That has to equal mass 2 times the acceleration of 2 in the x direction. The only force that I have acting is the tension, and that has to equal the mass, which is 4 kilograms, times the acceleration of 1.732 meters per second squared. So my tension ends up being 6.93 newtons. So I've now determined the tension. I want to point out that I could also figure out the normal force if I wanted. So the sum of the forces on 2 in the y direction have to be 0. So the ground acting on 2 minus the force of gravity has to equal 0. So I know the normal force is equal to the weight, so I could do that. I also could go back and I could look at just mass 1 if I wanted to. And I could make sure that the sum of the forces actually do add up the way that they should. I could check to see that I get the same tension that way, and I could draw a free body diagram that way. If I were to draw the free body diagram just for mass 1, so let's see if I have a little bit of space down here. So for mass 1, my free body diagram would have looked like this. I would have had a component of the tension, component of the applied force acting to the right, because that was acting on it. I would have had a component of the applied force acting up. I would have had the tension acting back, a component of the normal force on block 2, and then the force of gravity. I'm saying 2, and I mean 1, because this is block 1. Sorry. Ground on 1. And then the force of gravity of 1. And this is 6 kilograms times 9.8 meters per second squared. So we certainly could determine what that value is. And then we know that this system is accelerating. There's an acceleration of 1 in the x direction, which is exactly the same as 2. And if we apply Newton's second law, sum of the forces on 1 in the x direction equals the mass of 1 times the acceleration, we should get the same value for the tension within rounding error that we got above. So this would be 20 newtons times the cosine of 30 degrees minus the tension would have to be the mass, which is 6 kilograms, times the acceleration. And I don't have room to write the units. There we go. And I did not actually work out the numbers here, but I should get exactly the same number, and that's something that you could check.